One thing we can determine from Lewis structures is the molecular shape. We use a theory that's called Vesper, and I don't expect you to remember what it's called, but it stands for valence shell electron pair repulsion. I like to point it out because it actually sounds more intimidating than it is, but that's what Vesper is. Valence shell electron pair. So think about it. These first four words, valence shell electron pair, right there, are referring to the valence electrons. And then the word repulsion means to push away. So the Vesper theory, the idea is that all electrons are negative, and so the valence electrons will try to get as far away from each other as possible, because they repel. Remember, like charges repel. And from that, they determined what the shapes would be. And for many things, this valence shell, the Vesper model, does a good job at predicting the shape. Now, what it uses is Lewis structures. So we're going to have to use Lewis structures in order to determine the shape. And there's two things in the Lewis structure that we will have to look at. First of all, we will be looking at, let me erase that line there, and structure, look at I spelled it. Let's take a look. We're going to look at the central atom. So the atom that's in the middle of other atoms, the one in the middle. Now this is a disadvantage of Vesper because a lot of larger molecules, we're talking about a three-dimensional shape, and something that's larger could have lots of a chain of elements all in a line or in a row connected. And the Vesper model makes you look at each one like it was a central atom. So that is a challenge. It's not really great for big molecules. Although you can use it, it would just be like putting a puzzle together. So we're going to look at the central atom, and the two things we're going to look at, we're going to count how many atoms the central atom is bonded to, and we don't care if it's a single, double, or triple bond. And we're also going to count the number of lone pairs around it, and that's going to help us determine the shape. So for example, in the carbon dioxide right here, I would look at the carbon in the middle, and I see it has two atoms attached to it, 1, 2, and looking at the carbon, there are 0 lone pairs. Now I know there's lone pairs on the oxygens, but for Vesper, I'm just looking at the carbon atom. And we'll get back. This is a linear shape. I'll show you how we can determine it. Don't worry about that right at this moment. So let's look at the second example. So here's my central atom, the one in the middle. So I count how many atoms is it attached to? 1, 2, 3, 4. So it has 4 atoms. And then looking just at the central atom, it has no lone pairs on the carbon. Right? No lone pairs. I know there's lone pairs on the chlorine, but for the shape, we're just looking at the one in the middle. And this is tetrahedral, and I'll show you, and on the next slide I'll show you. There's a table that's in your book as a reference. This last example down on this page, I would look at the nitrogen, that's the one in the middle, and I see it has 1, 2, 3 atoms that it's bonded to, and then the nitrogen right there has 1 lone pair. So that's what it means. There's a lone pair on the central atom. This is something called trigonal pyramidal. So from this page, before you go on, I want you to look at these examples and make sure you understand what we're doing is we're looking at a central atom. We're counting how many atoms are attached to it, and we don't care if it's how it's attached, single, double, or triple bonds. And then on that same central atom, we're counting how many lone pairs are on it. Now, once we've done that, we can use this table, and this one is from your textbook. Now, this first column right here, this column, if I take this column and I add it to this column, I get this number right here. So that first column is not quite as important to us, but what you can see here, this column here has the number of atoms. Remember I said one of the things you want to look at is the number of atoms. And then the second column is the number of lone pairs, and that's what we also have to look at. And then that determines the molecular shape. So if we look back on this first example, it has 2 atoms and 0 lone pairs. So 2 atoms, 0 lone pairs is linear. I'm going to use a different color. This example here has 4 atoms and 0 lone pairs. Look, I have here tetrahedral. So here, this one has 4 atoms, 0 lone pairs, and it is tetrahedral. See, that's how we're getting the shape, by counting the number of atoms and the number of lone pairs. Now I'm going to erase this page because we're going to do some examples now, and I don't want to have all the writing on it. So let me erase it because we're going to use this page in a minute. And this is a table in your textbook. Okay, so in your homework you can see on these, and why don't you let me number these so I can call out a number for you. Now, for these examples, these are some Lewis structures, and you'll notice some of them have blue arrows. That's because when you have multiple central atoms, you have to be told which atoms you're going to look at or treat as central. So on some of the homework, if there's multiple atoms, they'll show you an arrow, and that's where they want you to do the shape. Okay, so let me take a look at the first one. So I would look at this carbon, and I see 4 atoms. I'm still looking at the carbon, and there are 0 lone pairs on it. So then going here, 4 atoms, 0 lone pairs, tetrahedral. So this guy is tetrahedral. Now number 2. So if I look at this guy, now number 2 I took out of a homework problem, and it also, sometimes you have to read the directions. You may have to add lone pairs. So remember from the beginning of this chapter, every atom has to have 8 except hydrogen. So when I look here, I notice that oxygen is missing 2 lone pairs. And when you're doing this shape, it's important, if the directions tell you to add lone pairs, to be sure to add them, because that will influence your shape. So let me take a look at this guy. So looking here, I have, if I'm looking at this first one, this carbon right here is attached to 4 atoms, right? There's 1, 2, 3, and 4, and 0 lone pairs. And so just like before, notice any of them that has 4 and 0, this is tetrahedral. We did that one on the last one, that would match. Now then the oxygen right here is attached to 2 atoms. And it has, around the oxygen, I'm looking, because that's what it's pointing to, 2 lone pairs. So let's look back. So 2 atoms and 2 lone pairs is bent. So this guy is, around the oxygen is bent. So even though I have it drawn in a straight line, it actually would have a bent, like it would have a carbon, then the oxygen, and then the hydrogen. It would actually have a bent shape. It would not be in a straight line. And the molecule wouldn't. In Lewis structures, I just drew it in a straight line. Okay, so let's look at number 3. So at this first carbon, I don't need any, this one, well, I could add lone pairs here, but I might ask you, why would that not change the shape? I mean, chlorine would need lone pairs because it doesn't have 8. But since the shape, we're looking around this carbon, those lone pairs won't affect the shape because we're only looking at the lone pairs around the central atom that we're looking at. So since I started with that one, let's just look. So that this carbon right here has 4 atoms attached to it and no lone pairs on it. I know they're on the chlorine, but that's not what we're looking at. We're looking at the carbon. So this is tetrahedral. And I didn't look back at that one because now I've done 3 different ones that have tetrahedral. And this carbon here is attached to 2 atoms, and it doesn't matter that one's a single bond and one's a double bond. It doesn't matter. It's just what it's attached to, and it has 0 lone pairs. So let's look back. So I need 2 atoms and 0 lone pairs. So 2 atoms and 0 lone pairs is linear. So let's try number 4, which is the one with the nitrogen. And you may say, well, why did you not put an arrow on that? Well, remember, sometimes it's only the central atom. And in this example, this is the central atom. There's not other atoms there. There's just one central atom. So if there's just one in the middle, they're not going to draw an arrow to it. Okay, it's just the central atom. So this nitrogen, it has 3 atoms attached to it. Whoops, I'm going to write it on the other side because I have number 5 and 6. So we have 3 atoms. Okay, it doesn't matter that one's a double bond, and 0 lone pairs. So then I go back and I have 3 atoms and 0 lone pairs, and that is trigonal or trigonal planar. Okay, so number 5. Let's do number 5. It has 2 different things here. So looking, I see sulfur only has 2 bonds. That's only 4 electrons, so it would have 2 lone pairs on it. Remember, it has to have 8, unless you're hydrogen, which only has a single bond ever. So we'll start there since I did that. So that sulfur has 2 atoms attached to it and 2 lone pairs. And so 2 atoms and 2 lone pairs is bent. And this carbon has, I'm looking at this one, there's 4 atoms attached, right? 1, 2, 3, 4, and 0 lone pairs, which this is a popular shape here. Anytime you have 4 atoms and 0 lone pairs, it's tetrahedral. And then finally, water, because I just really like water. So we know oxygen, that only has 4 electrons around it. So water has 2 single bonds and 2 lone pairs. There's no arrow because oxygen's the only thing in the middle. So this is 2 atoms and 2 lone pairs, which we've done that a couple times here. But 2 atoms and 2 lone pairs is bent. So water really, if I was drawing it, would not be in a straight line, but would rather have a bent structure. Now in the homework, sometimes they talk about angles. And I want you to know when they're talking about angles, this is a result of shape. So if they want to know about angles, what they're really asking you is about shape. So see, water has an angle that's about 109.5 degrees, which is all of these, anything with 4 total things around it. See all these have 4. You can see they're all right around 109.5.